Welcome to Whiteboard Wednesday. I'm Pierre-Xavier Thomas, Engineering Director at Cadence. Today I'm going to speak about the evolution of the ConnX DSP family, focusing on the B10, B20. We have a BB-EP series that have been used by our customers. And it has three members: the BB16 EP, the BB32 EP, and the BB64 EP. And they have been used, and they are used in LTE modem, LTE advanced modem, Cat-M, Wi-Fi, but also in radar FMCW and radar SAR system. Those DSPs are based on the VLI-W architecture, SIMD, which means that it has a single instruction operating on multiple data, or if you want, on a vector of data. So the differences between the BB-EP members are the size of the vector that is being processed for each vector instruction. So 128-bit, 256-bit, or 512-bit. We are extending our family, our ConnX family, by adding performance and adding features to go to the B series. We have two members, one with 256-bit vector and one with 512-bit vector. This family is targeted at new wireless standard, new wireless communication standard like 5G, but also higher resolution radar and lidar for radar imaging, for instance. We will talk about how we have been improving the performance and the features for this series. But before, let's go into the DSP processing that are being mapped on our DSPs in typical application. So in a PHY modem application, we have the input in the receive chain that are the IQ coming from the RF interface. So those are complex data, could be 16-bit, and they are going through the PHY modem, and the output are data channels, payload that are going into MAC layer. In the transmit pass, we have data channels coming into the PHY modem, and the IQ signals are also generated on the RF interface. The typical kernels that are mapped on our DSPs, that are processed by the DSPs, are FFTs, IFFTs, DFTs, FIR, correlations, power summations, some matrix multiplication, matrix inversions, but also some forward error connections, decoder, and some math. Some sine and cosine for phase tracking, or logarithm exponent as well. This is typically done into using 16-bit data types, but also looking into 32-bit data types and single precision floating point, or if you want the float 32 data type for more precision. As we are going into new standard, more throughput, more baseband bandwidths are being processed by the modem, and additional performance and features needs to be addressed. In the case of the radar sensor application, we also have IQ samples from the RF interface going into the radar sensor. And the output are typically detections with different coordinates in the space, x, y, z, but also velocity and potentially other type of characteristics. And this goes eventually into a decision layer, where various decisions are made based on the detection. So the processing that is being done in the radar sensors are similar with some dot product, FFT, some sorting algorithms, averagings for detections, but also some linear algebra for angle of arrival estimations, as well as some matrix inversion for Kalman filter in order to do the tri-ticking efficiently. Now, the data that are being processed in those applications are 16-bit, 32-bit, single precision floating point, but also half precision floating point, or the float 16 data type. So bringing this into our ConnX B series, what we've done in order to be able to address the higher resolutions and higher requirements for those applications is to raise the frequency. So the B series is capable of going into higher frequency thanks to a deeper pipeline and some optimized timing on the memory interfaces and cache interfaces. It's also capable of supporting more data types. So supporting natively the 16-bit data types, 32-bit data types, the float 16 data type, and the float 32 data types in order to be able to address the different precision requirements for those applications. Of course, we are still supporting natively also other data types like the 8-bit. We are also adding more capabilities in terms of processing elements for the Mac. So in that particular case, it's multiply accumulate for 16-bit and 32-bit data type. But also additional floating point capabilities with more FMAs for the single precision floating point, but also more FMAs for the half precision capabilities. We are also adding some other features like scatter gather for efficiently addressing random data in the local memories, which is also supported by our compiler efficiently. We also have some additional instructions for FEC decoder, and we have some improvement like this that are providing more performance and more features. Now, most of those features are also optional in order to be able to provide the right trade-off for performance over area, but also performance per watt. And so some of the options that you can see is that you have available is the 32-bit options, or also being able to select or not the single precision floating point, or the half precision floating point, or the scatter gather, or eventually the FEC decoder accelerations. So those are various options that are available to make the best trade-off for the system application. In summary, the B10, B20 DSP complement the ConnX DSP family by providing more features and more performance in order to address efficiently the various requirements of the new standard, wireless communication standard, and the high-resolution radar and lidar, by also providing native data support for those applications. Thank you for watching. See you next week.